The Sun has been particularly active lately, and it is about to undergo a fascinating and crucial change: the reversal of its magnetic field. This event typically occurs at regular intervals, around the midpoint of the solar cycle, and has significant implications for life on Earth. In fact, it is possible that, in the near future, the Sun could pose a serious threat that could lead to catastrophic disruptions globally. The Sun's magnetic field is generated by the movement of electrically charged gases within its core, a process known as the solar dynamo. Over time, this magnetic field grows increasingly complex and distorted due to the Sun's rotation and convection processes. Eventually, this cycle culminates in a complete magnetic reversal, where the Sun's north magnetic pole becomes the south and vice versa. Let's break down this process and take a closer look at the Sun. The Sun is primarily composed of hydrogen and helium in a plasma state, a form of matter where electrons are not bound to atoms, resulting in a mixture of free electrons and ions. Its interior is divided into several layers, with the core at the center, followed by the radiative zone and the convective zone. The core is the most important region, as it is where nuclear fusion occurs, converting hydrogen into helium and releasing vast amounts of energy. Above the core lies the radiative zone, where energy is transferred outward through radiation. In this area, energy moves slowly as photons are absorbed and re-emitted by the solar plasma. The outermost layer of the Sun's interior is the convective zone, where energy is transported by convection. Hot plasma rises toward the surface, cools down, and then sinks back, creating convection currents. The solar dynamo process primarily occurs in the convective zone, particularly in a thin layer known as the tachocline, which lies between the radiative zone and the convective zone. The tachocline plays a crucial role in generating the Sun's magnetic field, as it is here that the Sun's differential rotation and shear flows work together to create and organize magnetic flux. Here's something interesting that you might not have heard before. The Sun doesn't rotate like a solid body. Instead, different parts of the Sun rotate at different rates, with the equator spinning faster than the poles. This phenomenon, known as differential rotation, stretches and twists the Sun's magnetic field lines, amplifying the magnetic field. The solar cycle lasts about 11 years, during which the Sun's magnetic field undergoes several changes. At the beginning of the solar cycle, the Sun is in a state of solar minimum, characterized by a low number of sunspots and minimal solar activity. The magnetic field is relatively simple and bipolar, with distinct north and south magnetic poles. As the cycle progresses, the number of sunspots increases. Sunspots are areas of intense magnetic activity, where magnetic flux emerges from the Sun's interior. These sunspots appear in pairs, with opposite magnetic poles, and gradually move toward the equator as the cycle advances. At the midpoint of the solar cycle, the Sun reaches solar maximum, a period of peak activity marked by the highest number of sunspots, solar flares, and coronal mass ejections, CMEs. During this time, the magnetic field becomes highly complex and tangled due to the constant twisting and shearing caused by differential rotation and convection. As the solar maximum subsides, the magnetic field begins to reorganize, and the magnetic poles flip. North becomes south and south becomes north. This process is gradual and happens over time, but it's closely monitored by scientists using a variety of tools. Observatories on Earth and in space, equipped with powerful telescopes, capture detailed images of the Sun's surface and sunspots. Instruments such as the Solar and Heliospheric Observatory, SOHO, and the Solar Dynamics Observatory measure the Sun's magnetic field and track its changes. One key sign of an impending magnetic reversal is the behavior of sunspots. During solar maximum, sunspots become more frequent and pronounced, moving toward the Sun's equator, signaling that the magnetic field is becoming more unstable and preparing for the flip. Now let's take a deeper look at sunspots. As the Sun's magnetic field lines twist and tangle due to differential rotation, they suppress the convective flow of hot plasma from the Sun's interior, leading to cooler, darker regions on the Sun's surface known as sunspots. Sunspots are not only fascinating solar features but can also produce powerful solar flares and coronal mass ejections, CMEs. These phenomena release vast amounts of energy and charged particles into space. When directed toward Earth, they can disrupt satellite communications, affect power grids, and pose risks to astronauts in space. In addition to these hazards, increased solar activity can enhance auroras but also raise radiation levels in Earth's upper atmosphere. Now let's compare solar flares and coronal mass ejections. Both are intense releases of energy from the sun, but they differ significantly. Solar flares are sudden bursts of radiation caused by the release of magnetic energy associated with sunspots. These flares emit a tremendous amount of energy, often in the form of X-rays and ultraviolet radiation. The sun's surface can be likened as bright flashes of light and heat on the sun's surface. Coronal mass ejections, CMEs, are massive expulsions of solar wind and magnetic fields from the sun's outermost layer, the solar corona. These ejections can be thought of as enormous bubbles of gas and magnetic fields expelled into space. When a CME occurs, it releases billions of tons of solar particles at extremely high speeds. While solar flares and CMEs are related, they are not the same. A solar flare can happen independently, though sometimes an especially powerful flare may be accompanied by a CME. Though solar flares don't necessarily trigger CMEs, they can be linked in terms of their effects. Solar flares can disrupt radio communications, navigation systems, and pose a significant risk to astronauts due to the intense radiation they emit. On the other hand, CMEs tend to have a more widespread impact. They can cause geomagnetic storms that disrupt power grids, satellite operations, and create those breathtaking auroras. CMEs also increase radiation levels in Earth's atmosphere. While solar flares can be dangerous and destructive, CMEs generally pose a more significant threat on a larger scale due to their ability to affect Earth's magnetic field, which in turn endangers our technology and infrastructure. During periods of heightened solar activity, the amount of radiation reaching Earth also rises. Satellites and spacecraft are particularly vulnerable to this increased solar activity. The charged particles from the sun can damage electronic components, interfere with communication signals, and even alter satellite orbits. Aside from the harm to technology and infrastructure, the sun's magnetic field inversion, while not directly affecting Earth's atmosphere, can still have an impact. Some studies suggest that changes in solar radiation may influence Earth's climatic conditions, potentially contributing to climate change. For instance, increased solar activity can cause slight warming in Earth's atmosphere, exacerbating environmental changes. One of the most beautiful effects of increased solar activity is the auroras. These natural light displays, known as the northern and southern lights, occur when charged particles from the sun interact with Earth's magnetic field and atmosphere. While we often hear about the aurora borealis, these lights can also be seen around the South Pole. During periods of high solar activity, auroras become more frequent and can be visible at lower latitudes, providing stunning nighttime displays. However, besides the awe-inspiring auroras, there are concerning aspects of the sun's magnetic field inversion. One major risk associated with such events is the increased likelihood of geomagnetic storms. These storms occur when solar winds, laden with charged particles, interact with Earth's magnetic field. In extreme cases, they can lead to widespread power outages and significant infrastructure damage. One of the most notable events in history was the Carrington event of 1859. Astronomer Richard Carrington was observing the sun through his telescope when he saw a massive flare emanating from a group of sunspots. This solar flare triggered the most powerful geomagnetic storm ever recorded, with a coronal mass ejection, CME, directed towards Earth. The CME reached Earth in just 17.6 hours, an astonishingly short time given the sun's distance of 93 million miles. When the CME struck Earth's magnetosphere, it caused a geomagnetic storm of extraordinary intensity. The effect was immediate and widespread, disturbing Earth's magnetic field and inducing electric currents in the ground. Telegraph systems, which were the backbone of global communication at the time, suffered severe disruptions. Sparks flew from telegraph machines, operators received electric shocks, and some stations even caught fire. In some cases, operators could still send and receive messages even after disconnecting their batteries. One of the most remarkable outcomes of the Carrington event was the stunning display of auroras. These lights were so brilliant that they were visible far beyond the usual polar regions. People as far south as the Caribbean, Mexico, and Hawaii reported seeing the skies lit up with vivid colors. The auroras were so intense that they illuminated the night sky to the extent that people in the northeastern United States could read newspapers by their light. In the Rocky Mountains, gold miners were reportedly confused, mistaking the glow for dawn and preparing breakfast. Now, imagine if a solar storm of Carrington's magnitude were to hit Earth today. The consequences would be catastrophic. The Sun is undergoing a significant transformation, the reversal of its magnetic field, a process that occurs roughly every 11 years as part of the solar cycle. This event, driven by the solar dynamo, can have far-reaching consequences for Earth, potentially causing major disruptions and disasters. The Sun's magnetic field is generated by the movement of electrically charged gases within its interior, creating a complex magnetic field that eventually flips. The Sun is primarily composed of hydrogen and helium plasma, with energy produced through nuclear fusion at its core. This energy travels outward through the radiative zone and, later, by convection in the outer layers. The solar dynamo, which operates in the convective zone, is responsible for generating the Sun's magnetic field. Currently, the Sun is in its solar maximum phase, where sunspots and solar activity are at their peak. This increases the likelihood of solar flares and CMEs, which can disrupt satellites, communication systems, and power grids, and pose risks to astronauts. Scientists closely monitor the Sun's magnetic activity and sunspot behavior to predict when these magnetic field inversions are likely to occur. Sunspots, which result from twisted magnetic lines, can produce solar flares and CMEs, both massive energy releases that impact Earth in various ways. While solar flares emit radiation, CMEs release vast quantities of solar particles into space. These phenomena can enhance auroras but also present significant dangers to Earth's technology and infrastructure.